29 is about making electricity. We know back in 1820 that Hans Ørsted figured out, hey, if I have a wire, it's surrounded by a magnetic field. Well, that set scientists thinking that if a current can generate a magnetic field, isn't there some way we can use magnetism to generate an electric current? And about 10 years later, there were two scientists who figured out how to do this. An American scientist named Joseph Henry actually did it first, not a lot earlier, about the same time. But Michael Faraday was the first person to actually publish, and you hear Michael Faraday getting more credit for it, but really both of them did it more or less at the same time. They tried a lot of things, and what they figured out was a constant magnetic field does nothing, but a changing magnetic field can generate an electric current. One method, let me write this, a changing, and that changing part's really important, magnetic field through a loop of wire can generate, well, let's not say generate, let's say induce a current and an EMF. If there's current, there must be in the wire. Now, one method that you could do would be simply just, let's suppose that we have a galvanometer. A little pointy arrow that points to 0 in the middle there. And we take our little galvanometer and we make a few loops of wire. Connect the other end. Now, if all I do is take a magnet and I just stick a bar magnet through the loop, nothing's going to happen, because if I stick a bar magnet through the loop, I just have this constant magnetic field in the loop. But if I take a bar magnet, just a plain old bar magnet, if we were in class, I would absolutely demonstrate how to do this because it's easy to show. Remember, magnetic field lines are pointing out of this. They make those closed loops. So anyway, if I move this magnet back and forth like this, I'll see this needle move back and forth the same way. Okay. If I move the bar magnet in and out or toward and away from that loop, I'm going to generate a current. And this is called a galvanometer. It's a very sensitive ammeter. It just measures current. We'll see this. We call this process electromagnetic induction. All of the electricity that runs through our homes is generated on this principle of electromagnetic induction. We're not going to go into the real specifics of it. Let me grab my eraser. But that's the underlying principle. Okay. All right, which brings us to that sort of our introduction, the next section in our book. In section 29.2, it's called Faraday's law. But it really covers three real important ideas. They put an awful lot in this one section. The idea of magnetic flux, then Faraday's law, which tells us the induced EMF, it's for calculating induced EMF, and then Lenz's law, which tells us the direction. I'm going to try to get through the idea of magnetic flux and probably Faraday's law in this video. We'll do a separate video to talk about Lenz's law. Magnetic flux is very similar to electric flux. This is its symbol. Put a little B for magnetism. And it's equal to the perpendicular component of the magnetic field times the area, or B A cosine theta, or B dot A. Now remember, when we treat area as a vector, we're really talking about the normal to the area, okay? So that's a little bit different. If it's not just a simple area, we can rewrite this in integral form, in which case it's integral of the magnetic field to all these little infinitesimal areas. If we're not dealing with something that's plain and flat, a flat area, we might have to take that into consideration. Good. All right, let's look at this from a more sort of apply this idea. Oh, I should have probably wrote a little bit more. In those previous formulas, I'm going to write it in this form because I feel like this is the one we're going to use the most. B, of course, is the magnetic field, and that's got to be measured in Tesla. A is the area. So when we talk about flux, we always talk about flux as being sort of the amount of magnetic field lines through a particular area. And areas are going to be in square meters. And theta. Theta is the angle between B, which of course that's the direction of the magnetic field, and the normal to the area. Remember, when we wrote it in that integral form, we acted like the area is a vector. So when we treat area like a vector, the direction of that vector is that normal to the area. Like I say, it's just like if this area is this sheet of paper, the normal would be my marker. Like that. Okay, so what does that mean if we think about this? Well, it means we're going to get maximum flux when B is perpendicular to the area, or when B is parallel to that normal. If I get a different color marker, let's see, let's draw our magnetic field lines in blue. So if I have a magnetic field that points this direction too, I'm going to draw a piece of area first. There's an area, I've got some rectangular area. There's a normal to it. That's a perpendicular segment to it. If my magnetic field B points in this direction, and as you can see it coming out back there, there's all those magnetic field lines. I've got a nice uniform magnetic field. What you can see is, since the normal points in the direction of the magnetic field is parallel, B is parallel to that normal, or you can think of it as this area is perfectly perpendicular to that, we're going to get the maximum number of lines of flux through that sheet of paper. So in this case, it's just BA. Why? Because that's going to be cosine 0. Right? And if this is cosine 0, well, that's just 1. So the maximum flux occurs, of course, when the cosine theta is 1, that's the maximum value cosine theta can have. And that means that our area is perpendicular to our magnetic field. That's how we get the maximum amount of flux. Okay, that's not always going to be the case. Oftentimes, what we'll see is that our area is at an angle. So maybe this is our area. Our normal is going off like this. I don't know if I drew that very well, but I'm trying. There's some, it looks a little too. There's our normal. It's supposed to be making a perpendicular. I don't know if it looks very perpendicular, but I'm trying. Our magnetic field is still going this way. Notice we won't get as many lines if I tilt this back. I kind of want to tilt it more. Redraw that for you guys. There you go. That's a little more obvious. Here's our normal. Making. Now if I lay it down, some of those lines of force are going to go like this. It's not going to catch quite as many lines of force as it did before. If it doesn't catch quite as many lines of force passing through the area, then of course we get this flux equals BA cosine theta. Theta is the angle that this makes with the direction of the magnetic field. The magnetic field is pointing to the right, then theta is this angle between here and here. Notice it's not the same direction that the paper makes with, or the area makes with the magnetic field exactly. Okay. But we measure from the normal. Okay. Now, if I take that same area and I lay it completely flat, like this, now what we see is there are not going to be any lines of flux that actually pass through that area. The lines of flux will all either be above or below, but none of them will actually go through it if the paper lies or the area lies like this. In that case, what we find is when we put this in our formula, this is 0 flux. Because now when we draw our normal, you can see that the normal is perpendicular to B. This is going to be cosine 90. And we know that cosine 90 degrees is 0. So, but we can see it too. There aren't any lines of magnetic flux that are actually passing through that area. So, magnetic flux is basically the product of the magnetic field through an area. Okay? The more lines of flux or the more lines of that magnetic field you see passing through that area, the greater that magnetic flux is going to be. Oh, units. We know that this is Tesla. We know this is square meters. So it looks like our units will be a Tesla times a meter squared. But that does get a special name. It's a Weber. So we measure magnetic flux in a unit called Webers. Okay. Now that we know what magnetic flux is, we're ready to actually look at what Faraday's law says. law says that the induced EMF, and EMF is usually written with a cursive or a script capital E, is equal to the negative of the change in flux, or the derivative of the flux with respect to time. Now, there's a couple things I want to, that's for a single loop. Now, if you happen to have multiple loops, then we need to multiply that by big N for the number of loops. If it's 10 loops, we'll multiply the induced EMF by 10. And then the derivative of the flux with respect to time. Okay? This flux has to be a time varying quantity. One of the things I want you to realize is this negative is not terribly important if we're just trying to calculate the magnitude of the EMF. The negative is really directional. And when it comes to direction, we're going to use Lenz's law. So don't get too caught up in the negative. It's almost just as well if you just know that an induced EMF is equal to the rate of change of flux. Now, let's think about this. Flux is V A cosine theta. It's possible that you get an induced EMF because you have a situation where that is changing with time. It's possible you get an induced EMF because you have a situation where the area is changing with time. There are actually quite a few situations where you can vary that area. Or it's possible that the angle is changing with time. Most of the time when they induce electricity in big power plants, they have big coils of wire, turbines, what they call them, and they turn inside of a magnetic field. So they have a constantly changing magnetic field in the loop. If I had a magnetic field that went this way, but I have a loop here that's spinning, or a whole bunch of loops that are spinning. Some of the time, all of it's going through, some of the time, none of it's going through, but I will get that constantly changing flux. Where you see dams and where they use falling water, that water is actually used to turn the turbines inside of that magnetic field. Okay. So it's really important that we understand, first of all, this only has to do with direction. If we have more than one loop, we need to multiply by n, the number of loops, and we need to pay attention to which part of this in the problem is being actually changing. Now, this is an instantaneous kind of thing, DVDT. A lot of the problems are going to ask you for an average EMF from here to here. In that case, what you're going to have is you're going to have a situation where the average EMF is simply the change in flux over the change in time. It's not an instantaneous what's happening continuously. These are actually usually really easy to do. They'll tell you at t equals 0, you have this much flux. At t equal 10 seconds, you have this much flux. You can do a change in flux over change in time and see what that average induced EMF is. So let's look at an example. And this is in your textbook. I didn't write down a page number, but it's example 29.2. And in example 29.2, it says we have a square loop of wire. So here's a square loop of wire that it's 5 centimeters on each side. We have a magnetic field that's directed into the board. So here's a magnetic field into the board. Okay, so there's our square. It's sitting in this magnetic field. And they tell us that the magnetic field is a uniform 0.16 Tesla, and it's into this plane of the board. Okay? So what's our magnetic flux going to be? Well, it's pretty easy here. Our magnetic flux is BA cosine theta, but in this case, the normal would be parallel. If the normal is parallel, it doesn't matter whether we consider it to be at 0 degrees or whether we consider it to be at 180 degrees. Either way, that's going, well, we'll get a different sign. But we can treat this as 1. So the amount of flux through that loop, the loop is perpendicular to that, is simply 0.16, 0.05 meters squared. That's the area of the square. Cosine 0, and I get that the flux is 4.0 times 10 to the negative 4 Webers. Okay, that's part A. The second part says, what's the flux if B makes a 30-degree angle to A? Now, when they put that vector sign over A, what they really mean is the normal to A. Normal to the area. So, same formula. 0.16, 0.05 squared. There's B, there's A, but now we have cosine 30 degrees. So we find that now our flux has been reduced, and it's 3.5 times 10 to the negative 4th Webers. That makes sense. I know if I rotate while not perpendicular, I'm not going to have as many lines of flux through that area. So by rotating, we don't have quite as much flux. Okay. Part C, does part C? I thought there was a part C to this. Let's see. Oh, there it is. I just hadn't gotten out yet. Part C asks the question, okay, if this rotation from basically 0 degrees to 30 degrees took 0.14 seconds, and we know the resistance in that loop of wire, can we figure out, we know the induced EMF, can we figure out the current? So, hopefully you've got this, because I have to erase now. So, in part C, we want to do 2 things. If the time is 0.14 seconds, and that's between the first position and the second position, let's see if we can find the average EMF. Okay. And then, if the resistance in that loop there is 0.012 ohms, a loop of wire does not have a lot of resistance, we want to be able to see if we can find the current. We're just looking for an average EMF. So in this case, the average EMF is just going to be the change in flux over the time. I'm going to use the Even if we put the negative, we can turn that around. It's going to be 4.0 times 10 to the negative 4. That was the original. Here was the final. And the time it took for that to happen is 0.14 seconds. Normally we put final minus initial. There was a negative sign here. So I did initial minus final. I just reversed it. Okay. So if I put all of that in, I find out that my induced EMF is 3.6 times 10 to the negative 4. That's in volts. We are inducing an EMF for a voltage in that current, in that square. Okay? By rotating it, by changing the flux. The current, of course, is the induced EMF divided by the resistance. So 3.6 times 10 to the negative 4 volts, 0.012 ohms, and it comes out to be 0.030 amps or 30 milliamps. Okay, so that concludes our discussion about what magnetic flux is and what Faraday's law is. I suspect I'll have another example of Faraday's laws in one of these future lectures.